Okay, so this is my research about window queries over non-crossing line segments utilizing fractional cascading on directed acyclic graph structures. That title's kind of a mouthful, so it'll make sense when I start explaining. Okay, so what is a window query? So a window query is you have a bunch of input line segments of arbitrary slope, and then you have a vertical query line segment, and the reporting version is like tell me all line segments uh that intersect my query line segment. And the counting version is just how many line segments intersect my query line segment, right? So over here you can see it, right? So the query line segment is this red line, and then you ask like what line segments intersect it, right? And the first thing we notice about this is that like the input line segments, they form a directed acyclic graph structure, right? So what does this mean, right? So over here you can see like line 8 and line 7, right? And line segments 8 and 7, right? And they share x interval, or they share partial x interval, right? But at these x's, uh line 8 has a greater y than line 7, right? So we kind of say like 7 is less than 8, right? Because of this. And then over here, you have line segment 2, and we compare it to line segment 8, right? And they don't share any x's. So you can't really say, so there is no comparison between 2 and 8. But actually, we have line segment 4 over here, right? And 4 can be compared with 8, and it can also be compared with 2. So 4 also induces that 2 is less than 8, right? So this is just like a direct acyclic graph structure, and this structure can't have cycles because the input line segments are non intersecting, right? They're non-crossing. And yeah, so just keep this in mind. And we will take a topological sort of this directly acyclic graph, right? And then okay, so let's talk about Bentley's segment data structure. So this is a method, this is an existing method that my research will improve upon to for this problem. So let's see how Bentley solves this, right? So Bentley uses a segment tree, right? And he adds, and in his segment tree, he takes each of the input line segments and puts them in the segment tree one by one, so that in the segment tree, each input segment piece is broken down into at most log n pieces, right? So over here on on the right, this is the segment tree, right? So you can see it's like one node, two nodes, four nodes, right? And then we take like line segment 7, and it's stored here and it's stored here, right? And this makes sense because this is the representing like slices 1 and 2, and this is like representing like slice like 3, right? And what his and what his thing is, okay, he does is your vertical line segment, it has a singular x value because it's vertical, right? And that means that all you care about are actually nodes that lie on a path that contain this X region, right? So you see like the third slice is the one that contains the X, right? So you only care about like the nodes that contain the third slice, right? And this is a path on the segment tree, and there's only log n, right? Because that's the height of a segment tree, right? And on each of these nodes, you binary search for the first segment that intersects uh at each of these nodes, and then you go from there. So for each of these log n nodes, you have to perform a log n binary search, right? So that's a total of log squared n for a query, right? And my research, on top of that, we will add a fractional cascading, right? So again, we have a Bentley's data structure here in blue, right? So yeah, that's from the same from the last slide. And on top of that, we see we now have these like red numbers. So what are these red numbers? These red numbers is the topological sort of the we were talking about from before, right? But at each node, you only store the numbers that appear in the subtree in blue, right? So here it's like 1, 2, 6, 7, 9, 10 in red. Like here, as you can see, it's like 7, 2, 9, 1, 6, 10 in blue, right? And we also add red pointers to this as well. And these are fractional cascading pointers. So like for example, and it points to the first number that's equal to or greater than it. So 1 points to 1, 2 points to 2, 3 points to 6, 6 points to 6, 7 points to 7, 8 should point to 9, 9 points to 9, 10 points to 10, 11 is kind of a null pointer and so on, right? And then we also have these blue pointers as well, right? And these blue pointers, it's like it also it's within a node. It points from the red list to blues. Oh yeah, I mentioned this. The red is these pointers are from a node to its children, right? And the blue pointers are within a node, right? So, uh, red to blue, it's also the first number that's equal to or greater than it. So 4 goes to 5, 5 goes to 5, and so on, right? And now moving on to our key idea. The key idea is we just need to get the bottommost segment in our reporting query, and then we can index that in. So what does that actually mean? So again, we have our green query line segment, right? And the first, okay, we're gonna go bottom up, right? And the first line segment intersects is line segment 3, right? And how do we get that line segment 3? Well, actually, we could this is actually a point location problem. And what this and how we get line segment 3 is we use point location to find the region of our of the query segment's bottommost point, right? Which is right here. And the first line segment it could possibly intersect is the top boundary of the region from our point location data structure. From a point location, right? So point location would find this region, and this region, its top segment is line segment 3, right? And then from there, we take line segment 3 and we index it into our topological sort, right? At the root, right? And we follow all the pointers down, right? So 3 goes down to 3, and yeah, you just follow the pointers down. And what this does is this finds all the starting locations that we individually binary search for in Bentley's segment data structure, right? So as a recap, what we did is we perform one log n search, the point location search, right? And from there, like with all of one like pointers, we can find all the rest of the starting locations that we had to before individually like commit log n log n searches, right? But here we do it in a single log n search, right? So now the query time is just log n, right? And yeah. So and the key idea to like think about this and like convinced that it works is like it's back to the idea that like if two line segments share an X, like there's kind of like this like local ordering property, right? Where like if two lines share an X, then then the Y kind of forms a strict ordering, right? And like so even though the topological sort it's like you have like questions of like can like this segment can't necessarily be compared with this segment. You have enough that like it works out. Uh the storage and pre-construction are both n log n. And so let's look at previous methods. So we have Chisel's hive graphs. So what this does is this uses you kind of like traverse along regions, and then you kind of use like edge transitions to decide which region you go to next. But the problem is like it can kind of be like expensive. Like in this step, you're in this like fat region over here, and you're kind of like have a lot of choices to go to the next regions, right? And th that can be expensive, right? So Chisel, what he does is he like cuts the fat regions so that each of the there's only like two possible choices, right? When you go up, right? And that makes it so each edge transition is O of one, right? And this doesn't extend to count inquiries though, right? So then you have persistence. And persistence what it does is it kind of treats like you can think of this problem as like a bunch of like thin strips, and each of these thin strips is a binary search, is a it's a binary search tree, right? But obviously storing like a bunch of binary search tree for each of these red strips is like too much pre-processing and like storage, right? So actually you can think of this as a persistent balanced binary tree, right? And basically like at this first time it's like this, and then as you go rightwards for each of the strips, you kind of like update the tree. And then the persistence property allows you to go back and like query like for the strip you care about, like what it looks like, right? And that's what it's about. They and this method, it has the only different bound with my method is they have O of n size rather than n log n size for reporting, but for counting queries, it is all the bounds are exactly the same as mine. So my algorithm is tied with this algorithm, and I think these two are the best known for this for the counting problem, right? And then we have the trapezoidal search method, right? And the idea is that like basically like you kind of like this query segment, it's actually can kind of like be treated as like k point location queries, right? Where k is the number of like regions it intersects, right? And the idea is that like if you like compute these all at once simultaneously, the total path is actually not that big. The total path is actually only in log n plus k size, right? And again, this strategy does not extend to counting. So yeah, that's it.